Alright, this is the last lesson in our mini unit on conics. We're going to talk about something called the hyperbola today. That's the fourth of the conics that were created by taking that double napped cone and slicing it. So to begin, I want us to look at the equation of a circle, which is x squared plus y squared equals 16. That's this lovely picture, with radius 4. And now I'm going to say, what do you think happens when we change that plus sign to a minus sign? In other words, what in the world does x squared minus y squared equals 16 look like? Well, let's see if we find the domain first. So if we want to find the domain, I guess I have to solve for y. I'm going to actually do this. Negative y squared equals to 16 minus x squared. Or better yet, let's take the negative and distribute it to the right-hand side. So that's x squared minus 16. So if I want to solve for y, that just becomes the square root of x squared minus 16. And I'm thinking, for domain, when we have square root, the stuff underneath the square root has to be bigger or equal to 0. And I don't know if you remember how to do this from Math 11 or your previous courses, but there's different ways you can. You can either do a number line, or you can graph it out, whatever you wish. I'm going to do this and make a number line. I know that the places where it actually equals to 0 is at plus or minus 4. And then I don't know if you remember this method of splitting up the regions into 3 parts and testing if it's positive or negative. I can test by taking a value and plugging it in. Now I'm going to test 0. 0 squared minus 16, that's negative, so that's negative. Bigger than 4, I think it's 5, so 5 squared is 25. 25 minus 16 is 9, that's positive. And then over here it's also positive. So therefore, what's my domain? My domain here must be x has to be bigger than 4, or x has to be less than negative 4. That is my domain of this relation. Interesting. Okay. How do we find y-intercepts again? That's where you let x equal to 0. So 0 squared minus y squared equals 16. Negative y squared equals 16. Or y squared equals to negative 16. Huh? That can't be right. It is. That just means that there is no y-intercepts. Wow. So this graph here has a domain that's bigger than 4, less than negative 4, and then no y-intercepts. Okay. What about the range then? How do we figure out the range? Oops. The range. Well, the range is, I guess, looking at the possible y values. I think there's no really issue with the y values here, right? Y can be really anything. If you think about solving for x, I could say x squared equals to 16 plus y squared. X equals to the square root of 16 plus y squared. Well, is there any problems here with making this bigger or equal to 0? Nope, it works for everything, so therefore the range must be all real numbers. And then finally, what about the x-intercepts? That's when you let y equals 0, so x squared minus 0 squared equals 16, x squared equals 16. Oh, yes, we do have two x-intercepts, plus or minus 4. 4 comma 0 and negative 4 comma 0 are definitely points on this graph. That's good to know. I guess from here, let's go ahead and find some other points. So we found definitely when x is 4, y is 0. And negative 4 is 0. What happens when we plug in 5? Well, 5 squared is 25, minus 16 is 9, square root of 9 is 3. Notice it's actually plus or minus, so we get plus or minus. And I can do the same thing for all the other ones. So 6 squared is 36, 36 minus 16 is 20, square root of 20 is about 4.4, so I'll go plus 4.4. Same thing with negative 6. And then I'm going to ask you to fill out the rest of these, okay? And then after that, can you go ahead and try to plot these points, please? So, try it on your own. What's 8? 8 squared is 64, right? 64. Get my calculator. 64 minus 16 is root 48. What's root 48? That's approximately 7. I guess that's 6.9. 6.9 plus or minus 9, I think gives you something close to 8 or 8.1. 100 minus 16 is 84. Square root of 84. What's that? Square root of 84. 9.165. Sure. 9.2. And so now if we were to plot these points, let's see what happens. We got the point 4, comma 0 right here. Negative 4, comma 0 over there. Then at 5 you get plus or minus 3. Whoops. Plus or minus 3. So up here, down there. 6, 4.4. Oops, I should do the negative 5 as well, right? Can you see how this is going to be symmetric? 6, 4.4, negative 6, 4.4, 4.4. 7 is 5.7. Negative 7 is 5.7. And then 6.9 for 8. Close to 7, I guess. I don't think I even do the rest because it's kind of off the graph, but hopefully you see something like this. And it goes on forever and ever. This is called a hyperbola. Now notice that it has two distinct unconnected branches. The one on the left, a branch, the one on the right, a branch. Yet the branches are congruent. They are actually exactly the same, just a reflection. And that there is no curve at all in this interval in between negative 4 and 4. So there's nothing here. Nothing. Nothing. Okay? So, knowing this, I want us to look at one other thing called the asymptotic behavior. I want to look at how this graph behaves when x is really, really big. So we tried 100. Well, we didn't try. We're going to actually try now. 100 squared minus 16. And then we're going to take the square root of that. And the answer I got was like 99.9. 99.9 plus or minus. Next one with 1,000. If I do that, 1,000 squared minus 16. Taking the square root of that. Notice that 16 really doesn't make a difference. It's really small compared to that big number, but you get plus or minus 999.9. And if you continue to do the rest, I hope you see that that becomes 9,999, 99,999, and then 99999. Lots of nines. 6 of them, I think, this time. 1, 2, 3, 4, 5, 6. Yeah, 0.9. So really, what happens to the y values when x gets larger? It pretty much becomes plus or minus that same x value. Minus in that 16 really just doesn't do much to it, except maybe take off 0.1. So as x becomes large, the values of x squared become even larger. So thus the number 16 really is more and more insignificant. Who cares if we're subtracting 16 from like a billion gajillion dollars, right? You're still going to have a billion gajillion dollars. So that means as when x gets larger and larger, notice the value of the square root of x squared minus 16 gets closer and closer really to the square root of x by itself, because that minus 16 really doesn't come into play. So notice then in quadrant 1, the branch of this line gets closer and closer to this particular line, y equals x. And therefore, thus the line y equals, the line y equals x is an asymptote, hopefully you remember that term, of the curve. And notice that by symmetry, it must occur in the other quadrants as well because of this plus or minus. So you actually have two asymptotes, y equals x and y equals negative x. So I'm going to try to sketch that out as well on the previous page. So y equals x, and then negative x. Okay. Your asymptotes of y equals x y equals negative x. Asymptotes, once again, mean the graph gets closer and closer. So really, I should be able to like sketch this nicer and just draw the branch getting closer and closer to those two asymptotes. And there you go. Okay. So, I should say, note that the hyperbola can be written in the following form. Once again, I'm going to divide everything by 16. And if I divide everything by 16, I get this. And that's kind of handy because then it looks kind of like the equation of the ellipse, because everything has a 1 on the other side. And then I can rewrite the 16 as 4 squared. And so this is what they call the standard form of the hyperbola. So the standard form of a hyperbola at the origin is really, just this. X over a all squared. This time, though, subtract y over b all squared equals to 1. Okay? So, very similar to the ellipse. The only difference now is instead of plus, it's minus. And notice, once again, in this case, where a equals to b, where that horizontal expansion and the vertical expansion factor is the same, we have something special. It's just called a rectangular hyperbola. Really, I think it should be called a square hyperbola. I don't know why they called it a rectangular one, because it's not really a rectangle, it's a nice square. But whatever, that's what they did. That's what we'll do. So, on this page now, can you go ahead and use just what you've kind of learned and try to figure out the equations of all these hyperbolas? Yeah, this one's just really x squared minus y squared equals to 1. And this other one here would be x squared minus y squared. Yes, you can make this equal to 3 squared root of 9, or you can write it as x over 3 all squared minus y over 3 all squared equals to 1. Either or works. I actually kind of like the one that equals to 1, because it's more descriptive of all the expansion, compressions, and all that kind of stuff. So in this case for C, I would say, hey, I believe the equation would be x over 2 all squared minus y over 2 all squared equals to 1. And once again, these are all nice rectangular hyperbolas. Okay, now you're thinking about D. What happened to D here? If you wrote down x squared minus y squared equals to 1, that's exactly the same as A. But the graphs are not the same. What's different between A and D? The asymptotes seem to be the same, yet the branches are now no longer opening left and right, they are opening up and down. So how do you think that affects our equation then? Because when it opened left and right, we had these nice x-intercepts. But when it opens up and down, now we have y-intercepts, but no longer x-intercepts. So what can you do to find a y-intercept of 1? That's when you let x equal to 0. And if I let x equal to 0 right now in this equation, I got a problem. So really what has to happen here is that the y value has to be positive and the x value has to be negative. Or you write down a negative 1. So really there's two situations here you can have. You can have this. You can have a y squared minus x squared equals to 1. Or you can write the equation as x squared minus y squared just like before. But now you need to make this equal to negative 1. Both of these are correct. I don't care which one you use, but I kind of like having the y one in front, because I know this is up and down, so I always think y. So y squared minus x squared equals to, in this case, 3 squared, which would be 9, or I'll say y over 3 all squared minus x over 3 all squared equals to 1. And then similarly for f, notice that it's expanded by a factor of 2 in both the y and the x. So I'll get something like that. Okay? Alright, those were all rectangular ones. Now we're going to mess you up because we're going to make the expansions and compressions a little bit different on the horizontal and vertical. So I want to see if you can actually put all this stuff together now. I want to see if you can do G, H, I, J, K, L yourself, and then come back and check your answers with mine. Go. Remember, G, H, and I, they all open left and right, so the X goes first. Where J, K, and L, the Y's go first because it opens up and down. That's 2. Oops! Y first. Good. And once again, those dashed diagonals are called the asymptotes. So really this hyperbola is really the strangest looking shape that we've done in this section. It kind of looks like two back-to-back parabolas, but really they're not exactly parabolas because they do get closer and closer to these asymptotes. So let's turn the page and let me just quickly show you what the real definition, the proper definition of a hyperbola is. A hyperbola is similar to the ellipse. It's the set of all points in a plane such that the distance from the point to one focus minus the distance. Remember how the ellipse was the sum? This time it's the minus, and that's why this is the minus sign. So the distance from the point to one focus minus the distance from the point to the other focus is, again, a constant. Okay? So the only difference is one critical change. I replaced the word plus with the minus, which is what I actually did with the equation, if you think about it. I changed the plus to a minus. Okay? You can read through this yourself. This is trying to show you where the concept of a hyperbola came from and how it could be applied. But to save some time in the video, I'm just going to try to go and fill in this. Okay? Let's just focus in on these two parabolas, G and K. And I want us to look at the equation of the hyperbola, the value of A, which is the expansion in the horizontal, the value of the B, and then also think about something called the equation of the asymptotes, those dotted lines. So I think for G, once again, we're going to write down the equation of the hyperbola, x squared minus y over 2 all squared equals to 1. And for K, I think we had y first, so y over 2 squared minus x over 3 squared equals to 1. Notice the value of A is always the denominator or the expansion factor of the horizontal. The value of B in this case is the factor of the vertical. So there's 2. Similarly here, the factor of A is the horizontal, okay, and B is the vertical. Can you see what the equation of the asymptotes are now for both G and K? So think back to the equation of a line. Slope, yeah, rise over run. Notice it's like 2x. And also the other way is negative 2x. So y equals to positive 2x or negative 2x. And then similarly for K, what do we have here? Rise is 2, run is 3. So y equals to 2/3 x. Y equals to negative 2/3 x. I want you to focus on this value of the slope and how that's created from the values of A and B. Can you tell me? Can you tell me? Can you tell me? Yes, it does look like the slope really is just the value of the expansion in the vertical B divided by the expansion in the vertical A. Okay, so let's see if we can summarize this now. There are two types of hyperbolas, once again. Okay. Equation in the standard form with center 0, 0. I want us to write that out. That's just really standard x over A all squared minus, once again, y over B all squared equals to 1, because, once again, the A value is the horizontal expansion. The B value is the vertical. The equation of the asymptotes, what we just found out, is just the plus or minus of B over A, which is the slope times x. Remember, the vertices are the ones that actually are part of the branches. So in this case, the value of a comma 0 and negative a comma 0. And then we have major minor axes, right? Sorry, we have something called the transverse axis and the conjugate axis. The transverse one is the one that touches the vertex. So in this case, it's the horizontal one. Its length is 2a. The conjugate is just the other axis that doesn't touch the vertex. That would be 2b. And once again, if I were to change it into standard form, shifting it to coordinate h and k, then we should plug in that shift as well when I graph, or not graph, when I write out the equation. Done. And the asymptotes, well, the asymptotes are a little bit different because then we have a different point. So y minus k equals to plus or minus b over a x minus h. This is the point slope form. If you don't like that, you can just write it like this instead and move the k to the other side. And there you have it. Okay. Now, what about the one that is opening up vertically? In the diagram here, I don't really like what they did. I'm going to actually ask you to change it. I prefer to keep the a value always as the x. So you can cross out this stuff too. Cross out, cross out, cross out, cross out, cross out, cross out. And then similarly, if I did it like this, then the, whoops, what did I just do? The y goes in front. Then you're subtracting the x, and that equals to 1. The equation of the asymptotes now, once again, become plus or minus b over ax. The vertices, however, now are 0, comma b and 0, comma negative b, because now the hyperbola opens upward and downwards. The transverse axis, that changes because that's the one that touches the vertices. It's 2b now, and the conjugate is 2a. And once again, if I were to change the equation and shift it to h comma k, y minus k then over b all squared, minus x minus h all over a all squared equals to 1. And similarly, I think the equation of the asymptote is still the same. Okay, so this is a good summary of all the things you need to know about the hyperbola. And now let's try to apply these things. All right, number 1, sketch the graph. Hard to sketch when it's not in that nice form, so once again, let's do it. Let's make it that nice form. 4x squared minus y squared. I'm going to move everything to, not everything, but the constant to the right hand side. We must divide everything by negative 16, so we get here negative 4x squared over 16 plus y squared over 16 equals to 1. I'm going to rewrite this as just y over 4 all squared minus, and this simplifies to x over 2 all squared. And now we're ready to graph because I'm still going to have the center at 0, 0. I'm going 4 up for the y and 4 down for the y, 2 to the right for the x, 2 to the right for the x. And this time, instead of drawing the ellipse, oops, that's not the question we're doing, I'm going to ask you to draw a dotted box. I like to do the box. Okay, and then I'm going to ask you to connect the diagonals, because these diagonals are actually your asymptotes. Yeah, y equals to, what is it, 4 over 2, so 2x, and y equals to negative 2x. And because we know that this is a parabola that opens up or down because the y starts first, the vertices must be here and here. And then to do the rest, you can make a table of values or just politely sketch a branch that gets closer and closer to those asymptotes. Done. Okay. So very similar to the ellipse. That's why I spent so much time on that. And now you can do the hyperbola. All right, here's example number 2. Determine the coordinates of the center, the lengths of the transverse and the conjugate axes, and then also the coordinates of the vertex and also the coordinates of the foci. Oh no, let's not worry about the coordinates of the foci. And that will be enough. Okay. Notice this case. Ooh, -1. Trying to trick you again. Okay. But nonetheless, not a problem if you write it like this. Y plus 3 over 16. Oops, I should actually change that for you as well. Make it 4 squared. Yeah, remember? 16, 4 squared. 9, 3 squared. Nasty. Notice in this case the center coordinates are going to be 1, -3. 1, -3. And I know I'm going to draw my box now going 3 to the right. 1, 2, 3. 3 to the left. 4 up. 4 down. Box. 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 Draw my diagonals. Asymptote, 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 asymptotes. And then because this is once again one that starts with Y, we know the vertex is on the top and bottom of the box. And then here we go. Perfect. Coordinates of the vertex then we know must be what? 1, comma, how do I go up? 1. And then 1, -7. The transverse axis, that's the one that touches the vertex, has a length of, it's the vertical, so 2 times 4, which is 8. The conjugate axis then has a length of the other one, so 2 times 3, which is 6. And anything else I need? Probably the equation of the asymptotes. I'll do it for you anyways. Y equals to the slope is 4 over 3 plus or minus x. And oops, I forgot this is point slope form, so y plus 3 x minus 1. And if you want us to solve for y, there you go. All done. Okay. So finally, let's ask you to try example number 3. I want you to consider this conic section. Under what conditions do you get a circle, and what conditions do you get an ellipse, and then in what conditions do you get a rectangular hyperbola? See if you can think about this really quickly yourself first, and then come back and I'll give you the answers. Okay, you're back. Circle, hopefully remember this. That means A must equal to C. Yes, these values must equal to C in order for you to get a circle. How do you get an ellipse? Well, remember the A value cannot be equal to C, because if they are the same, then you get a circle. But you also need to understand that both of those have to be the same sign. So either both of them are positive or both of them are negative. Usually we write this like this. The two things multiplied together must be bigger than 0. And under what conditions do you get a rectangular hyperbola? Well, rectangular hyperbola is a square one, so that's really when A equals to C. But this case for hyperbola, it's no longer a plus sign that separates these two terms, it's a minus sign. So when I multiply them together, you get AC must be less than 0.